early 1944, Wright Field, Dayton, Ohio. A test pilot gripped the throttle of a P-51B Mustang as he pushed past the standard war emergency power setting. The engine thundered as boost pressure climbed to 75 inches of mercury, fueled by a new experimental blend labeled simply as Grade 150. The airspeed indicator climbed beyond numbers that marked the previous peak for Allied fighters. At 25,000 feet, the Mustang surged through 448 mph test engineers on the ground, exchanged looks as the radio carried the pilot's updates. This was no minor improvement. It was a revolution wrapped in purple-tinted aviation gasoline. A chemical advantage so significant it would render obsolete every assumption the Luftwaffe held about American fighter performance. The war in Europe was poised to shift, and the driving force was not a new aircraft or a tactical innovation, but a fuel that enabled existing planes to achieve levels that defied German expectations. Unknown to the Luftwaffe, American and British fuel chemists had created something the Third Reich's synthetic program could never match. While German fighters labored on B-4 fuel rated at 91 octane on the lean mixture scale, and their top C-3 fuel barely approached the performance of Allied grade 130 fuel, American refineries were producing aviation gasoline with a performance number of 150. The impact was immense. A P-51 Mustang using standard 130 grade fuel could reach 437 mph at 25,000 feet. That same plane, flown by the same pilot at the same altitude on a 150 grade fuel, could surpass 448 mph. German fighter pilots, who had come to respect the Mustang's range and high-altitude ability, were about to find that the Americans had fundamentally shifted the rules of air combat. The Messerschmitt Bf-109G, the Luftwaffe's main fighter in early 1944, had a top speed of 400 mph at altitude. The Focke-Wulf 190A could reach 408 mph under ideal conditions. Against Mustangs on 130 grade fuel, German pilots could attempt engagements on somewhat fair terms. Against 150 grade fuel Mustangs, they faced a disadvantage no amount of skill or clever tactics could overcome. The story of this advantage starts not with the war, but with peacetime petroleum chemists who understood that octane rating measured how much an air-fuel mixture could be compressed before spontaneous detonation. Higher compression ratios produced more power per combustion cycle. More power meant faster planes and higher operational ceilings. The science was simple, but producing high-octane aviation fuel at industrial scale was extraordinarily challenging. By 1940, as the war raged in Europe, American aviation fuel production was focused on 87-octane gasoline. This sufficed for commercial planes and early military trainers, but was inadequate for high-performance fighters. The British, desperate to gain any edge against the Luftwaffe's numerical superiority, collaborated with American oil companies to develop 100-octane fuel, available just in time for the Battle of Britain. The difference was immediate. British Spitfires and Hurricanes using 100 octane gained 30 out of 40 mph more speed at altitude, with climb rates improving by 500 to 1,000 feet per minute. German pilots, previously dominant on 91 to 100 octane fuel, now faced parity. The creation of 130 grade fuel represented the next leap. With a performance number of 130 on rich mixture settings, it became the backbone of Allied air power through 1943. It powered Merlin engines in Spitfires and Mustangs, Allison engines in P-38 Lightnings, and the massive Pratt & Whitney R-2800 radials and P-47 Thunderbolts. Production scaled quickly under aviation fuel advocate General James Doolittle, who had spent the 1930s lobbying both military and oil companies to invest in high-octane fuel development. By 1943, 17 Allied refineries were producing high-octane aviation gasoline using the catalytic cracking process perfected by French-born engineer Eugene Houdry. American refineries alone were producing millions of gallons monthly, enough to support the massive bombing campaigns over Germany and the growing fighter forces providing escort. By contrast, German fuel production was constrained by their dependence on synthetic fuel derived from coal. The Burgess process that converted coal into aviation gasoline was technically effective but slow and resource-intensive. Even at full capacity, Germany could produce only a fraction of the high-octane fuel flowing from American refineries. Most German fighters ran on B4 fuel rated at roughly 91 octane on the lean mixture scale. Premium C3 fuel, primarily for BMW 801-powered Focke-Wulfs and select Messerschmitts, was roughly equivalent to Allied grade 130 fuel, but in very limited supply. By 1944, perhaps two-thirds of German aviation fuel production was C3 grade, yet this still represented only a small portion of what the Allies were generating. Understanding how fuel performance works begins with a basic principle of internal combustion engines. Octane ratings indicate how resistant a fuel is to detonation. As a piston compresses the air-fuel mixture during the compression stroke, temperature and pressure rise sharply. If the fuel ignites on its own before the spark plug fires, it causes detonation, an uncontrolled explosion instead of a controlled burn. This creates shockwaves that can damage or destroy engine parts. Fuels with higher octane ratings can endure more compression before detonating. By definition, octane ratings do not exceed 100, because 100 octane represents the detonation resistance of pure isooctane, the reference standard. Performance numbers go beyond this, measuring how much more compression a fuel can tolerate compared to isooctane. A fuel with a performance number of 150 can withstand 50% more compression before detonating. Producing such fuel required adding anti-knock compounds, mainly tetraethyl lead, and carefully blending aromatic hydrocarbons such as toluene and xylene with base gasoline. British chemists at the Royal Aircraft Establishment tested numerous blends throughout 1942 and 1943, searching for the optimal mix of anti-knock properties, energy content, and practical manufacturability. At the same time, American researchers at Wright Field conducted parallel experiments and shared findings with their British counterparts. By early 1943, both nations had created experimental batches of what became known as a 150-grade fuel. The label was slightly misleading, implying an octane rating of 150, which was chemically impossible. In reality, the fuel had a performance number of 150 on the rich mixture scale, while maintaining 100 octane performance on the lean mixture scale. Dyed purple for easy identification, it underwent extensive testing throughout 1943, and the results surpassed expectations. Merlin engines running on grade 150 fuel could sustain manifold pressures of 75 inches of mercury, compared to 67 inches on 130 grade fuel. This translated directly into increased horsepower. The Packard Merlin V1657 engine powering the P-51D Mustang produced 1,490 horsepower at standard military power on 130 grade fuel. The same engine on 150 grade fuel at war emergency power in the P-51B with the V1653 variant reached 1,220 horsepower, effectively about 1,600 horsepower. Flight tests at Wright Field confirmed significant performance gains across all regimes. Maximum speed increased by 25-30 MPH at altitude, and climb rate improved by several hundred feet per minute. Crucially, these gains required no modifications to the aircraft. A Mustang flown one day on 130 grade fuel and the next day on 150 grade fuel became noticeably faster and more capable, simply due to the fuel. The decision to deploy 150 grade fuel to operational fighter squadrons was made in early 1944. Timing was deliberate. The 8th Air Force, based in England and conducting daylight bombing raids deep into Germany, was suffering unsustainable losses. Although the first P-51 Mustangs arrived in December 1943, German fighters were still inflicting heavy casualties on bomber formations. American planners needed not only long-range escort fighters, but fighters fast enough that German interceptors could not evade or refuse combat on favorable terms. In May 1944, The first operational deliveries of 150 grade fuel arrived in England. Distribution was carefully controlled. Not every squadron received it immediately. The 8th Air Force prioritized select units to manage supply and evaluate combat performance. The RAF, which had pioneered much of the testing, also began equipping squadrons with the new fuel. Priority went to high-speed interception missions, especially against German V-1 flying bombs threatening London in June 1944. The V-1 flew at around 400 mph at low altitude, where air density reduced aircraft performance. Tempests and Spitfire 14s could barely intercept them. Mustangs on standard fuel were marginal. Mustangs on 150 grade fuel had enough speed to intercept reliably. On June 18, 1944, Major R.E. Turner of the 356th Fighter Squadron destroyed a V-1 by tipping its wing with his Mustang, a technique repeated at least 16 times during the campaign. This required extreme precision, positioning the fighter's wing within 6 inches of the V-1 and using airflow to roll the bomb off course. The first widespread combat use of 150 grade fuel coincided with the Normandy invasion. 8th Air Force fighter groups flew combat patrols and bomber escorts using the new fuel. German pilots began reporting encounters with Mustangs performing beyond previous experience. Luftwaffe intelligence collected these reports describing American fighters that could evade German interceptors in any flight regime and seemed to have power reserves defying explanation. Initially, these accounts were dismissed as exaggeration or pilot error. Intelligence officers reasoned that German pilots, tired, outnumbered, and facing mounting losses, were misreporting. However, this assessment was incorrect, and the true impact of grade 150 fuel would only be fully recognized after the war. Garrel, a Luftwaffe ace credited with 275 victories, mostly on the Eastern Front, flew missions against American aircraft over Germany in 1944. In interviews conducted during the 1970s and 1980s, he recalled being astonished by the performance of late-war Mustangs. Later, R would test fly-captured American fighters, including the P-51, P-47, and P-38, and noted that the Mustang stood out for its speed, climb rate, and high-altitude capability. What R and other German pilots did not realize in combat was that they were facing an aircraft chemically enhanced beyond its original design specifications. Mustangs were operating at power settings that their engineers had never intended. The Merlin engine, designed by Rolls-Royce and manufactured under license by Packard, was carefully engineered for thermal limits, bearing loads and detonation margins. Using higher boost pressures pushed these limits closer to the edge. The revolutionary aspect of 150-grade fuel was that it allowed engines to run at extreme power settings without catastrophic detonation, which would have destroyed engines running lower-grade fuel at the same boost. This capability relied on a precise chemical interaction between fuel molecules, air, heat, and pressure in the combustion chamber. Tetraethyl lead, the main anti-knock additive, disrupted the chain reactions that caused premature ignition. There were trade-offs. Tetraethyl lead was toxic, requiring careful handling by ground crews, and it left deposits on spark plugs, valves, and cylinder walls, increasing maintenance needs. 150-grade fuel, with its high lead content, accelerated these issues. Fighter units experienced more frequent spark plug fouling and increased cylinder wear. American maintenance protocols adapted quickly. Spark plug replacement intervals were shortened, cylinder inspections became more frequent, and engine overhaul schedules were adjusted. Despite the extra maintenance, the performance benefits were deemed worthwhile. For pilots, using 150-grade fuel required new operating procedures. Manifold pressure limits were raised, and pilots had to avoid overboosting, especially at low altitudes where air density was higher. Managing fuel consumption became critical. Although the fuel offered more power, running at full boost rapidly consumed fuel. Long escort missions, such as to Berlin and back, already pushed the Mustang's range to the limit. Pilots had to carefully decide when to use maximum power and when to throttle back to conserve fuel. Combat reports from summer and fall 1944 show the impact of the new fuel. 8th Air Force units equipped with 150 grade fuel reported higher victory-to-loss ratios and improved ability to intercept German fighters threatening bomber formations. German pilots who once could strike quickly and escape found themselves unable to outrun Mustangs. On August 6, 1944, Lieutenant Hollis Bud Neylan of the 357th Fighter Group, flying P-51D Hellsbells with 150 grade fuel, engaged a Messerschmitt Bf-109 piloted by Guy Schack over Eastern Europe during Operation Frantic Missions. Neylan's speed advantage proved decisive. He quickly closed in and damaged the Bf-109's cooling system. Running low on fuel and ammunition, Neylan broke off pursuit, waving to the German pilot before returning to escort duties. Schack managed a belly landing near German lines. For decades, Schack wondered why the American pilot hadn't finished him off, unaware that Neylan had assumed the aircraft was only damaged. When historians later reunited the pilots, Schack confirmed that the Mustang had performed beyond anything he had previously seen, with speed and power reserves, unlike any other American fighter he had encountered. The psychological effect on Luftwaffe pilots was significant. Already outnumbered and facing superior Allied forces, they now faced Mustangs with seemingly limitless performance. Their tactical choices narrowed. They could mount mass attacks hoping numbers would prevail, avoid combat to preserve aircraft and pilots, or engage and risk being shot down by faster, more maneuverable Mustangs flown by increasingly confident and aggressive American pilots. Reichsmarschall Hermann Göring, commander of the Luftwaffe, famously remarked upon seeing P-51 Mustangs over Berlin that he realized the war was lost. This reflected the strategic dilemma. The Mustangs' long range meant that no part of Germany was safe from daylight bombing. The arrival of 150 grade fuel in mid-1944 worsened this crisis. Luftwaffe Technical Intelligence eventually acquired samples of Allied 150 grade fuel from captured drop tanks or crashed aircraft. German chemists analyzed the samples and confirmed what Luftwaffe pilots had been reporting all along. American engineers had developed aviation gasoline with performance far beyond the capabilities of German synthetic fuel. Some German sources suggested that late-war C3 fuel occasionally approached a performance level of 150, but production was limited and quality inconsistent. Allied bombing raids on German synthetic fuel facilities, particularly attacks on Luna and other major plants in May and June 1944, further restricted fuel availability. By late 1944, the Luftwaffe was rationing fuel. Fighter units were prioritized, yet they still operated under strict limitations. Training for new pilots was drastically reduced, leaving many German aviators with minimal flight experience, while American pilots typically had several hundred hours of training before entering combat. From January to May 1944, before widespread use of 150 grade fuel, American bombers experienced loss rates of roughly 3 to 6% per mission, sustainable but painful. After the introduction of 150 grade fuel and the Allies' attainment of air superiority, from June to December 1944, loss rates dropped to under 2% per mission. Fighter victories rose sharply. P-51 groups across the 8th, 9th, and 15th Air Forces claimed around 4,950 German aircraft destroyed in air-to-air combat between late 1943 and May 1945, with many of those victories occurring after June 1944. The experienced German pilot force, though battle-hardened from the Eastern Front, was gradually eliminated. By D-Day, June 6, 1944, only 2 Luftwaffe planes appeared over the Normandy beaches. Germany still had thousands of fighters, but fuel shortages, a lack of trained pilots, and limited tactical flexibility made effective deployment impossible. The technical specifications of 150 grade fuel were remarkable. Its lean mixture octane rating of a 100 allowed engines to cruise efficiently without detonating, while the rich mixture performance number of 150 could withstand 50% more compression than pure isooctane at maximum power. This combination let pilots fly long distances efficiently, then switch to full power settings for combat with confidence that the engine would not fail. Due to the high tetraethyl lead content, handling procedures required strict precautions. Ground crews wore protective gear, cleaned spills promptly to prevent lead poisoning, and clearly marked fuel trucks and storage tanks to prevent accidental mixing. Despite these measures, safety incidents were rare. Introducing 150-grade fuel to operational squadrons also required pilot training. Pilots learned the new properties and updated engine operating procedures. Manifold pressure limits were increased, and operational guidelines detailed when and how to use maximum power. No aircraft modifications were needed. Engines and fuel systems were fully compatible with both grades, simplifying logistics. Production figures highlighted America's unmatched industrial capacity. Between May 1944 and April 1945, the 8th Air Force used over 53 million gallons of 150-grade fuel, while overall Allied production likely exceeded 200 million gallons. Each gallon required refining infrastructure, chemical additives, quality control, transportation, storage, and distribution to airfields. In 1944, American industry operated at near-miraculous levels. Thousands of bombers, tens of thousands of fighters, Liberty ships launched faster than Germany could sink them, and oil refineries producing more aviation gasoline than Germany's total output across all grades. This resulted from decades of industrial development, abundant natural resources, a homeland safe from bombing, and a workforce including millions of women who took factory jobs to support the war effort. The Royal Air Force also used 150-grade fuel extensively. British squadrons flying Spitfire 14s, Tempest Vers, and Mustang the 3s and Ivies received priority allocation. RAF pilots reported similar performance gains to American pilots. The Tempest, already one of the fastest piston-engine fighters, became even more formidable. Between June and September 1944, RAF Tempest units shot down 638 V-1 flying bombs, with No. 3 Squadron alone claiming 305. Squadron leader Joseph Berry shot down 59, Belgian ace Remy van Liarde destroyed 44, and Wing Commander Roland Beaumont took out 31. Other successful interceptors included the Mosquito, 623 victories, Spitfire 14, 303, and Mustang, 232. The advantages of 150-grade fuel were evident in every mission. Fighter groups using it reported higher victory counts and fewer losses. By March 1945, nearly every P-51 unit was operating on the new fuel. Reports from this period show overwhelmingly one-sided engagements. German fighters rarely challenged Allied formations effectively, and when they did, they suffered heavy casualties. By April 1945, missions over Germany often met no aerial opposition. The Luftwaffe had been destroyed by attrition, fuel shortages, and the systematic loss of experienced pilots who could not be replaced. On May 8, 1945, Germany surrendered, ending the air war in Europe with complete Allied air supremacy, a supremacy built on multiple factors, but critically enabled by unmatched industrial production and advanced aviation fuel technology. The P-51 Mustang's long range proved vital. American pilots were exceptionally well trained, and Allied forces held overwhelming numerical superiority. Yet one of the most decisive advantages came from petroleum engineering, specifically the 150-grade fuel. This purple-tinted gasoline transformed already capable fighters into extraordinary machines, boosted pilot confidence, and embodied the combined technological and industrial power of nations able to outproduce, innovate, and ultimately outlast their adversaries. In aerial combat, speed is critical. A faster fighter can dictate the terms of engagement, choosing when to attack and when to disengage. It enjoys tactical freedom that slower opponents simply cannot match. When American aircraft gained significant speed through a combination of advanced airframe design and superior fuel, the Luftwaffe's tactical choices became severely limited. By late 1944 and early 1945, the disparity between German and Allied situations was stark. Allied fighters could fly multiple missions daily, constrained only by pilot endurance and maintenance schedules. German aircraft, in contrast, often remained grounded due to fuel shortages. When they did fly, strict conservation measures curtailed their combat effectiveness. A German pilot who expended too much fuel during a sortie might not have enough to return safely. Allied pilots, however, could use full power when necessary, confident that fuel reserves would safely carry them back. This operational flexibility had profound strategic effects. Allied fighters maintained constant patrols, responded to threats aggressively, and sustained continuous operations. German pilots had to choose engagements carefully, conserve fuel meticulously, and sometimes break off combat. Not because they were losing, but simply because they risked running out of fuel. Luftwaffe airmen lived each sortie with the knowledge that it might be their last, not due to enemy fire, but due to insufficient fuel for another mission. Allied pilots, on the other hand, flew with confidence rooted in material advantage, fast aircraft, abundant fuel, and a strong support to infrastructure. This assurance encouraged bolder tactics, improved combat outcomes, and higher survival rates. The story of 150-grade fuel is ultimately a story of industrial warfare. Victory favored the side that could produce not just more aircraft, but superior aircraft. Not just adequate fuel, but fuel that gave a decisive performance edge. Not just trained pilots, but a surplus of skilled aviators supported by an industrial base capable of replacing losses faster than the enemy could inflict them. The work of American and British fuel chemists, conducted in laboratories and refineries far from the battlefield, never involved facing enemy fighters or anti-aircraft fire. Yet their efforts, measured in performance numbers, manifold pressure readings, and chemical innovation, helped determine who would control the skies over Europe in 1944 and 1945 each. Time a P-51 pilot advanced his throttle and felt the Mustang surge ahead with unmatched power. He was reaping the benefits of chemical engineering that had turned crude oil into a fuel capable of making extraordinary performance routine. German planners had expected American fighters to operate within predictable limits based on their airframe design and standard fuel. Instead, they faced aircraft that outperformed every calculation, fueled by a production system so extensive and advanced that Germany could not match it. By spring 1945, as Allied forces swept into Germany from east and west, the Luftwaffe had effectively ceased to exist as an organized fighting force. Some units still flew, often with barely enough fuel for a single mission. Jet fighters like the Me-262 represented a technological leap, but they arrived too late in insufficient numbers and were hampered by fuel shortages and the absence of experienced pilots, systematically eliminated in combat. The final tally underscores the cumulative impact of Allied advantages. American P-51 groups across all theaters flew hundreds of thousands of sorties, claiming roughly 4,000 to 950 enemy aircraft destroyed in the air and another 4,131 destroyed on the ground. These numbers reflected not just aircraft losses, but also the depletion of trained pilots, lost experience, and wasted German industrial effort building replacements that were destroyed before making a strategic difference. While 150-grade fuel was not the sole reason for this outcome, it was a critical factor. It provided the edge that turned close contests into decisive victories. A P-51 properly fueled to achieve 448 MPH represented not just speed, but a combination of technological superiority and industrial capacity that German planners had not foreseen. Fuel chemists and petroleum engineers, working far from the front lines, had created a weapon as effective as any gun or bomb. Purple-tinted gasoline could shape aerial combat as decisively as superior tactics or advanced pilot training. The secret to Allied air dominance in 1945 rested on the compression ratios of piston engines, the anti-knock properties of carefully blended hydrocarbons, and the unmatched performance numbers of aviation fuels Germany could not replicate. The P-51 Mustangs flying over Berlin in early 1944 were remarkable aircraft. The Mustangs over Berlin in early 1945 were the same machines, but fueled with a gasoline that made them faster, more powerful, and more capable. That difference, measured in octane ratings, performance numbers, manifold pressures, and airspeeds, was one of the many factors that determined control of Europe's skies. In this outcome lay the fate of Nazi Germany and a vivid demonstration of Allied industrial strength. A purple liquid, pumped into fuel tanks, burned in powerful engines, and turned into victory, one mission at a time.